Nah, di sini mungkin. Oke, assalamualaikum warahmatullahi wabarakatuh. Okay, good morning, everyone. Okay, today we have Professor Dr.
Sorry, I can't hear you. Hello? Hello?
Pak Bu, excuse me, Professor Yatima. It looks like the connection for Pak Bowo is having
problem, eh?
Yeah,
Okay.
problem.
Okay, just let me know because I
Yes,
can't hear
Professor.
anything. Yeah.
Yes, Professor.
Still no connection?
Yes, he's working on it. No.
Okay. All right. It's okay.
Because in the second floor in our department, sometimes the internet connection having a problem, so he's
I see. Okay.
using another room in the department.
Okay. All right. Understand.
Hey, Bang. I'm really sorry, Prof. For
Okay. It's okay. Understand.
connection.
All
Okay,
right.
today I will begin. We'll begin the lecture then. Okay, today we have Professor Dr. Yatimah Alias, for our guest lecturer in the electrochemical methods. Yeah, she will be delivering the lecture for 3 days, and this is the first day, about the electroactive layers and modified electrodes. So I hope you guys, students in Indonesia, will get more benefit, will get more knowledge from our distinguished professor. Okay, and yeah, just a little bit introduction for our guest lecture today. Yep, Professor Yatima is a Vice Chancellor for Academic and International Relations in the University of Malaya. She was graduated from University of Malaya for BSc and MSc, and University of East Anglia, UK, for her PhD. And her areas expertise is sensors, sensors, electrochemical sensors, biochemical sensors, glucose sensors, ionic liquid as well, and also coordination chemistry. So That's just a brief introduction for our guest lecture today, and she has a lot of awards and very yeah, a lot of publications. I think you all guys are very fortunate to have Professor Yatima here for our lecture. So without any further ado, oh yeah, maybe there is opening remark from our department, head of department, professor, before your lecture. So Asep, are you there?
Okay.
Asep will be giving opening remarks. Okay, thank you.
Warahmatullahi wabarakatuh.
Waalaikumsalam.
Very pleasant good morning to each and every one of you. Thank you for being with us today for the student, and also Pak Rahmat Wibowo, Pak Muhammad Ridwan. Would like to show my sincere appreciation to you both. So this UI result program is possible to be conducted today, and my high appreciation to Professor Dr. Yatima Alias, yeah, as our guest lecture in lecture series, yeah, in the topic electrochemical method. So I'm sure that, as Pak Bowo mentioned before, that based on Professor Dr. Yatimah Alias experience and knowledge, yeah, will be shared with you all students who attend this class. So we will extend, yeah, our horizon in understanding the electrochemical method, especially for today topic is electroactive layer and modified electrode. And we will see soon, yeah, from Professor Dr. Yatima Alias, how this lecture will combine the finding of his research in this area, also with the concept, yeah, of the electrochemistry in general. So the student will have understand the good data, the experimental method, and how it produce the quality of data research. So on behalf of Department of Chemistry, again, I would like to say thank you to Professor Dr. Yatima Alias. Demikian Pak Bowo, terima kasih. Waktu saya kembalikan kepada
Thank you, Pak Asep.
Bowo.
Okay, so without any further ado, please, Professor Dr. Yatima, for your lecture. Okay, thank you. I will turn off my camera, Prof.
Okay, it's okay. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and good morning to all. Thank you very much to Prof. Asif, Head of Department of Chemistry, and Dr. Rahmat Wibowo for introducing a little bit of my curriculum vitae. And I think I would like to special thank to Prof. Ivan, who actually invited me to join the virtual classes with the students in UI. So thank you very much to her. And I think it's a privilege for me to actually contributing on this virtual lecture to students of third year who is actually majoring in chemistry. So thank you very much. And I think this session will be more on the sharing session with the students, and I hope active participation from the students. So before we start, basically this is going to be a lecture, it's not a conference paper. I would appreciate if the students, themselves should be asked asking questions to me if they would like to have more clarification on certain of the topics. Okay, so very much appreciate on that one. So I'm continuing my lectures in English. All right, I think it's going to be easy for us to understand more, especially on the terminology, all right, used in electrochemistry. By training, I'm actually electrochemist. I've actually had an experience working in quite a broad research area, especially looking at some advanced material for certain application. So in particular, for sensor technology, but at the same time, I'm also exploring in coordination chemistry, looking at a bigger picture of coordination compounds, and where we can also include or embed some ionic materials in a macromolecule. So that's where my research work is all about. So today, specifically on the course of electrochemical methods. So we have a few topics. I've been given by Prof. Ivan to actually share with you on the topic of electroactive layers and modified electrodes. So if the students look at the topic of the subject matter, we are talking about electroactive, means we want the material who actually can possess electron. And if you look at here, we are concentrating on layers because most of the material that been produced, we're going to stack as layers so that they have space for electron transfer in between the layers. So that's why most of the advanced material that looking at it, we are concentrating on layers, okay, to produce the conducting materials. And on the other side of it, we are also looking at modifying electrode surface, because we know that when we talk about electrochemistry, we are working mostly on heterogeneous condition where we have electrodes and we have solution. So in this particular case, to look at the interfacial reaction, so we are looking at surface of electrodes. So we can modify the surface of electrodes. So that's where the topic of electroactive layers and modified electrodes. Move on to the second part of it. So I just want to share, I've been given 3 slots of lectures, okay? So today will be the first one. So we call it first session. But the first session, I'll be covering on the main topic of electroactive materials. And we shared some introductions and we going deeper into the different kind of materials. Okay, when we talk about electroactive materials, very broad actually, yeah. So we are targeting on more conducting materials, okay, because we want them to be electroactive. The second session of the lecture will be on the modified electrodes. This is more on the fabrication part, okay, looking at how we can fabricate and modify and design the electrodes. And then we move on to some characterization, okay. And finally, we are looking at more on the application. So the most applicable for these studies, I'm going to share on the sensor, okay, and some of our work that related and some examples that can be given to the students, how we can actually relate the first, second towards the third lecture, okay. I hope this will give some overview of what I'm going to cover on this particular lecture hours, okay. Is it okay so far? Students, can you understand? Students? Hello?
Yeah, okay.
Yes, Miss.
Yes. I hope that the students be more participating in this lecture, because I think this is more on the students' part. At least I want to know that you understand or need a little bit of explanation on certain part, okay? Okay, so move on. Okay, I just want to go very briefly on some introduction. I think you have actually covered this during maybe in your second and your first and second year, talking about electrochemistry as general subject. And from what I've seen, there are a few lectures in the beginning from these electrochemical methods where you're covering voltammetry, potentiometry, because these are the electrochemical method that's covering, okay, looking at how we can understand the electrochemistry reactions, okay. So basically focusing on electrode reactions. So if you look at the right-hand side of the diagram, this is a typical electrochemical reaction setup, okay, where you have either 2 electrode system or 3 electrode system, depends on the type of measurement that you're going to measure. If talking about maybe potentiometry, you are looking at 2 electrode system, or you're talking about voltammetry, you're using a 3 electrode system. But if you look at there, 3 important electrodes must be there, which we call it working electrode, WE, and we have reference electrode, which is very near to the working electrode, to make sure that the potential that being measured, you know, at the positions less resistance from other factors. And we have counter electrode because in a general electrochemical system, we must have anode and cathode. So basically, in most of the electrochemical methods where we do measurement, especially on the electroanalytical technique, we must have 3 electrode systems. So then if we connected to the system, okay, to the potential stat, which actually you can do some changes in terms of potentials or current depending on type of measurement that you are doing, either potentiometric, voltammetric, conductometric. So you will use electrochemical workstation, okay, that combine with the computer system so that you can do some analysis. So these are typical setup, okay, when we do electrochemistry studies, okay. So I hope that this one is quite general, but you know, this is very important because later on we will looking into more details, okay, on this. And if you look at the yellow on below of the working electrode, this is where we can do modified electrode. Okay, we have electrode, but we can do a modification on the surface of the electrode. Because on a typical type of working electrode that we use in class, for example, we use like glassy carbon electrode, we are using a gold electrode, platinum electrode. It's just a bare electrode. But when we're talking about modified electrode, you will modify the surface of that electrode. Okay, so this is where we're going to look into more details on this particular topic. So when we talk about electrochemistry, I think that the left-hand side, it is actually give you some background of it. But what important here, we know that when we study electrochemistry, we are talking about interrelation between electric and also chemical effects. Okay, so we are talking about interfacial, where we know that electron, okay, from the conductor, okay, can reduce the ions, either oxidize, reduce, or oxidize the ion. So then the surface of the electrode is very important. Okay, that's why we must make sure the surface of electrode must be clean, must have a homogeneous surface. Okay, must make sure that, you know, the surface very smooth and so on. So every time when we do electrochemical studies, we need to polish the surface of the electrode. Okay, because we want to make sure that the reaction happen at all surface area that being covered. Okay. So then the other one is we are looking into the study, you know, more on mechanism studies of the reaction, but all the mechanism studies will be looking into the whole electrochemical system, okay, including what happened on the ionic transport in terms of the electron transport. So we are looking both at electron transport as well as chemical transport. That's where we are studying about mass transport and so on. So what important here to understand the electrochemical studies is to look at the interconversion between chemical energy and also electrical energy. That will give you more understanding of what happened on the surface of electrode. Okay, so this is very important for us to understand the overall system, because when you talk about or do some design of the electroactive materials, that will give you more understanding of how this material can actually interconvert between chemical energy and also electrical energy. Okay, but overall, when we do electrochemical reaction, we are looking into how they can produce current, or how we can change the potential to produce current, how we are looking into the state or the condition of the reaction, whether it's equilibrium or whether, you know, is spontaneous reactions and so on. This will give more input in terms of kinetics studies, in terms of electron transfer studies, and that will give you some ideas how this will relate to the mechanisms of the reaction. Okay, why we need to study electroactive materials? Okay, when you talk about materials is you can have different material. You can have material, solid material. You can have semi-solids material. You can have polymers. You know, different kind of materials. But what we are targeting here in this particular topic, because we are talking about electrochemical methods, we are looking at electroactive materials. Okay. So these electroactive materials is very important, especially in the current science and technology, because if you look at your handphone nowadays, you know, that's the best that you can see, you know, directly. You can see that they are using battery, okay, because we want to make sure that the battery lasts long, the battery can be charged and recharged, okay, and can be used for quite some times, you know. They are using this technology, okay, whereby in this particular case, they must make sure that the material used in handphone is electroactive, okay, and the material can last long in certain conditions, especially temperature. We're talking about temperature. We are talking about pressure, okay. We are talking about type of materials, you know, preferably to be physically solid, okay. Second one, we are looking into why we need to study or we need to understand about electroactive materials, because they have a wide range of applications, sorry. Okay, so as I've given you the first example just now, it's about your handphone. Handphone, like I said, you have battery, you know the battery consists of electrodes and electrolytes, okay. So we know that in this particular case, we are looking at electrodes and also membranes, okay. The membranes where the layer of electroactive layers play an important role for energy conversion, okay. So in this particular case, we are talking about electrodes and membrane, okay, definitely applying for electrochemical device, okay. So when we talk about electrochemical device, definitely it involves energy conversion, okay, and storage, and looking at more devices and like sensors, because sensors is a detectors, okay. Nowadays, quite number of sensors, not only focusing on electronic devices, but also in certain industries like food industries, okay. We want to make sure that the sensor can detect certain chemical contents, or we can also use sensor for environmental studies, okay, like looking at pollutants, water pollutants, you know, chemical pollutants and whatnot. And then on the other hand, there are also a lot of application in supercapacitor, diodes, you know, transistors, okay, and other things. So that's why electroactive material is very important, especially in a form of solid, okay. And in this particular case, when we're talking about electroactive materials, we are looking into materials that is very flexible, capable of changing size and shape with varying electrical field, because the application is so broad, from the lower energy to higher energy, from lower frequency to higher frequency, and from a different duration of usage. That's very actually looking at more materials. So that's why it is very important. And the other one, okay, that looking at that kind of material is a unique properties, okay. Why is it unique? If you're talking about only materials, okay, you can see from your bare eyes that you can see a solid material and whatnot. But in this particular case, we are talking about electroactive, you know, which is conducting materials. So in this case, we are looking at unique properties such as high mechanical flexibility, low density, simple, okay, simple, easy handling, and no acoustic noise, no low cost, and others, okay. So these are some of the factors, you know, that taken into considerations why the electroactive material studies is of interest of most of the developing countries, okay, because it relates with technology, okay. We relate with technology. We're talking about computer, we're talking about gadget, we're talking about handphone, we're talking about, tabs and other things. So that's very much related to the behavior of these materials. Okay, just to give you some ideas, all right? When we're talking about these conducting materials, give you some ideas. What are the materials that we are talking about? Okay. First, I think every one of you know about carbon base. Okay, we have the main topic about materials about carbon base. Okay, but this carbon base, if you reduce or oxidize, or if you change the geometry of the carbon, they will make more conducting carbon. Okay, that's where it will be giving you a more electroactive materials in that sense. Okay, and the other component of material that we are looking at, I'll give you some examples later. It's called, okay, so these are that been generally used, okay, generally modified and tunable, is like polypyrrole, polyaniline, and a lot more. Later part, I'll give you more examples. Okay, the third material that we are looking at, we call it metals. Metal is common, like what I'm saying much earlier. When we use a common electrode system, it's a metal, okay, like platinum, gold, okay, copper. So this is just a pure metals. The other modification that we made on the metals is called metal oxide. So it means we oxidize the metal, or generally it can form as metal oxide that, on the earth, you can have plenty of metal oxide that be ready. So we can use that as well as our materials. The other one is a bimetallic system. And now this is not only bimetallic, we have trimetallic and tetrametallic system as well. Because once the research go on, they would like to look into, designing high density of materials that can cover more than 2 metals in there. So they go from bimetallic, trimetallic, and so on. The other materials, they call it 2D materials. The 2D materials is also one of the one of emerging fields in electroactive materials, like molybdenum disulfide, because they have a lone pair electron. That is very important. When you talk about electroactive materials, they must have space, they must have porosity, they must have electron covering them. So that gives them more the electron density around the materials. So these are the different types of electro materials that I'm going to go more details with the students. Okay, then you can understand more about different type of electroactive materials. So why we need to study these electroactive materials? Generally, if you look at the main factor, all right, that we are looking at, definitely we want to have materials that are non-toxic. Because if we are dealing with issues that need to cover to make sure that we protect the material. So what we are looking on these electroactive materials, it is non-toxic definitely, but the most important, they can show high sensitivity, sensitive to detect or to give response, okay, to certain condition. High selectivity, also important, especially when we talk about sensor later on the third lecture series. I'll talk about selectivity. And then high durability, definitely you are looking at the current condition. We want our devices durable, okay, can stand at the long hours or can stand at different temperatures and conditions. So we need to have high durability. On the other side of it, when you want to design that, definitely you need to have a fast response time. Okay, you don't want to wait. Okay, I know that when every one of you looking at 4G, 5G, of course you want to go for more because you want to have faster response time. Same as the material, because they made from material. The fiber optics also made from materials. The the wire also made from materials. So we have to make sure that we choose the right materials for that particular application. And we want also to have long-term stability, okay, because when we have some materials that being produced or being designed, it should give us more stability. Okay, we want it more stable. We don't want to have material who actually prone, okay, if temperature change drastically, they cannot stand and they can just compose or decompose. or maybe, some changes in terms of chemical structures and so on. So we don't want that. So we want a long-term stability. And definitely, sorry, it's not low cost, it's a low cost. It's low cost. Sorry for the mistake, it's low cost. Definitely you want a material which actually not spending a lot of money. Okay, it can save a lot of money. So what I'm going to cover in this lecture as a whole, okay, I'll share with you different kind of materials, okay, different type of materials. As been given much earlier, that we're going to look into different type, okay, either carbon, polymer, metals, we are looking into different combinations of metals and so on, from micro to nano size materials. But I think to have the higher surface area, we need to have much lower in terms of size, and we are talking about nano size nowadays. All right. So then this is what we're going to cover on the materials part. On the other hand, we are talking about fabrications. Okay, fabrications or the synthesis method. It depends on the materials that we're going to produce on that. Either we do, normally we always compare chemically and also electrochemically, because we are electrochemists. So every time when we do this, we want to compare how we do it chemically, how we do it electrochemically. Because when you talk about chemical reaction, I know that every one of you have gone through organic chemistry, and some organic chemistry synthesis involve like 17 steps, for example, 17 steps. But when we do electrochemical study, we can reduce to only 1 or 2 steps only. Okay, so that will give you more understanding on how this can be done in different fabrication methods. And finally, we are looking into sensor. That's where, to be more specific on the application side. Before I go to more deeper on this electroactive materials and layers, okay, I'll just give you one example. This is what we do in-house, which is actually in chemistry department, University of Malaya, where one of my PhD students did this, where looking into different synthesis method to produce silver nanoparticle, carbon nanotube, and reduced graphene oxide composite. If you look at here, it consisting of metal, which is silver nanoparticles, and then we are using carbon base, which is carbon nanotube, and then at the same time also another carbon base, which is reduced graphene oxide, and we do a composite. And in this particular preparation, we use 3 different fabrication methods or 3 different synthesis methods. One is, we call it hydrothermal. Okay, the other one we can do it through electrochemical methods, and another, finally, we can also do via chemical methods. So we have a different type of synthesis method that we can use, but at the end of the day, we can have the same silver nanoparticle, carbon nanotube, reduced graphene oxide composite. So this is very interesting studies, okay, whereby you do a combination and also combine to make composite, but using different synthesis method. This is one of my PhD students last time who actually achieved these studies, and then we can see a different type of nanomaterials produced from these silver nanoparticles, carbon nanotube, and reduced graphene oxide composite. So this is very important, okay, for us to understand how this combination of composites can happen from different type of materials. On the other hand, I want the students also to understand why we need to look into electroactive layers and how we're going to do it. These are also one of the examples, okay? If you look at this, these are also done by my PhD students here in University of Malaya, where in the beginning, when you look at here, they try to prepare the silver nanoparticles and reduce graphene composite. And this preparation on the A synthesis part, they are using hydrothermal. This is a combination of different type of synthesis. So first, they are doing a synthesis using hydrothermal. Second, when they want to use the polymer, the conducting polymers, they will use sonification method. This is method. So the sonification, and then they got a pani. Okay, so the pani is actually the polyaniline. Okay, and then when you do the C, which is we're talking about electroactive layers. Okay, they do layer by layer deposition. Okay, so first layer deposition, they are using a bare electrode, which is glassy carbon electrode. This is a common working electrode used, okay, for a simple electrochemical studies. And the first layer, the first drop they are putting in is the first synthesis, is the hydrothermal, where you produce a hydrothermal silver nanoparticles, reduced graphene oxide. So you put the first layer. Then the second layer, the second drop, they use the second method, which is done by sonification. And they put the pani, all right, the polyaniline. And then finally, when they try to do a modified electrode, you can see the reaction between silver nanoparticles and pani, and they can produce the electroactive layers. So these are what we call it final modified electrode. So we can do a different combination of material to get a final modified electrode. So these are the whole spectrum of understanding, you know, before we go deep into one by one, what type of material, but I would like the students to understand why we call it electroactive layers on the surface of the modified electrode, because the bare electrode, the main electrode that used is actually the GCE. On top of GCE, we put another electroactive layers consisting of silver nanoparticles, reduced graphene oxide, and also conducting polymers. So until now, is the students okay with that? Any comment? Any comment by the students, or is it too tough? I'm not sure. Are you okay with that? I hope you understand.
So far, I think it's okay, Prof. Yatima. I think the student can listen. Yes, yeah.
Okay, Dr. Yuni, sorry.
Yes, yes,
okay,
yeah.
I hope they can understand, because I go one by one so that they can understand the flow.
Yes.
So, all right. Okay, thank you very much. So I shall proceed with that. Okay, so we go to the first examples of materials, okay, because this is very important, because as I mentioned much earlier, when you talk about electroactive materials, we talk about electroactive layers later on, and you talk about modified electrode. We want to make sure that the material used, one, definitely give you conducting behavior. You want to have a conductor, okay, because that is one of the criteria when you do electrochemical studies, okay. So how can you tune them, or how can you modify, or how can you make them more conducting, okay? Because when I talk about conducting material, I know that you, hopefully you have actually gone through this. We used to study conductivity, okay? Conductivity, when we start in our first year, we use a pH meter, all right? So pH meter is actually an electrochemical, an electrode, okay, that use the concept of electrochemistry. So that's basically to study the concentration of each class, okay? So that use potentiometric measurement, okay? All right. So if you look at that, the electrode themselves, all right? When we want to design the electrode materials, we are looking into the best electrode which is conducting. So using pH meter is just, or you can conduct conductometer mostly is under the condition of liquid. You mean the target analyte in terms of liquid. But nowadays, a lot of research being studied. If you're looking into a high impact publication, or most of the recent studies related to science and technology, they are looking at more solid conducting materials. Okay, so then we're talking about solid conducting material. This is where I'm going to give you more example on the solid materials. Okay, so the first one, as I mentioned, is a carbon base. Okay, carbon base, you know, is either a trigonal, tetrahedral. Okay, because we have carbon with another 4 carbon, which is like a diamond shape and so on. So carbon actually can be formed into different dimension. Okay, we're talking about first, second, third dimension and so on. Okay, and they can form a different type. For example, we're talking about one dimensionally carbon base is actually carbon nanotube. Okay, we also have 2D carbon, which is on graphene And when we talk about 3D is in form of graphite, even we can oxidize it to become a graphene oxide, or we can have diamond shape, which is very strong diamond shape. So, but carbon is, I think, the most available material, okay, that is considering cheap, but when you convert it to different dimension, then it becomes a bit expensive. But why they become a bit expensive? Because of the geometry, because of the electron availability, and because of the conducting behavior of this material make them more expensive. Okay, but carbon base is important. We can say that is very much studies being done because they have excellent dispersibility, okay, in water and solvents. So the condition that given on specific application or studies is important. The media is very important. That's why when you talk about the selected materials, it should have excellent dispersibility. The other one, because of the size of this, and it gives a high surface area. Okay, you can see from here again, you can see a lot of space in between, you know, that give a high surface area to the material. And then the carbon base also is easy to mix with polymers. That's why when I give you one example of my students' work, they combine with silver nanoparticles with also polymers, okay, pani, okay, polyaniline. So it's easily being mixed with different polymers and can be deposited easily on any substrate. So the example that I given to you before this slide, where the substrate is actually the electrode, which is GCE used, and then you can easily deposit it when you have a combination, because people talking about combination of materials to form composites, okay, that will give you a way forward, you know, to deposit in a best way. So when we're talking about graphene, okay, which is based from carbon, okay, graphene is the ultimate two-dimensional carbon molecule with outstanding properties. Because if you look at graphene, they have high electric conductivity, high thermal conductivity, excellent optical properties, and chemical properties. This diagram shows, you know, this is also done by my students. You know, she did a graphene oxide and thin layer of graphene oxide from a solution, drop casting, okay, drop cast on the surface of just a petri dish, and you form a thin film of graphene oxide. And this graphene oxide have high electrical conductivity, thermal, okay, it lasts, you know, in a quite a good temperature, high temperature, and give you optical. Optical mean you can see through. It's very transparent. Okay, depends on the size of your thin film, and they have a different types of chemical properties. And if you look at the structure of graphene oxide, it's a lot of oxygen, okay, and carboxylate group around the carbon base. So this is where it is very important. So this sometimes called a functionalized carbon-based material. You functionalize them, you know, it's not only carbon, but they have hydroxide and oxygen group, so that they give you more options, especially in terms of electron density of the material. So this will give you a lot of advantage, you know, when we start collecting electroactive materials, then you look at these possibilities of giving you a graphene oxide. So the graphene oxide, there are quite a number of synthesis method as well. You can do either chemical synthesis, and you can also do either electrochemical synthesis. This is what we do it in our laboratory. And the other one that we also do is to modify the graphene oxide. Okay, so to modify the graphene oxide, so some preparation can be done. This is a chemical synthesis preparation. If you look at here, we use a reagent from graphite, the normal graphite, which is graphite is cheap, all right? But using a different reagent, so you can have a graphite oxide. And by changing the pH, all right, you can see a different formation of graphite oxide, either layers or single layers or smaller portion of graphene oxide. Then it gives you a more different size and different layers, and also different condition, okay, to give you different size of the nanomaterial. Because after this preparation method, like for this example, we do a chemical modified methods. Okay, you can send for some characterization to look at the final outcome of your nanomaterials. So this give you some ideas of how the reagent, okay, using a normal chemical synthesis, you can actually get the graphite oxide. The other carbon-based material that we are looking into is called a carbon nanotube. Okay, carbon nanotube. So these are the typical diagram of carbon nanotube. But if you look into this SEM, all right, more into the micrograph, you can see that it's a long hollow carbon. Okay, so this is where it depends on the different size of the diameters of this carbon nanotube. That's why different synthesis method, different condition, either chemically or electrochemically, you can have a different size of diameter. So you can actually measure different size of diameter, different size of the carbon nanotube. And the other one, we also can produce a multi-wall carbon nanotubes. Okay, you can see a multiple row layers of graphene sheets, and you can see two different layers, of the graphene, and where we can have a multi-wall carbon nanotubes. So carbon nanotubes also one of the electroactive material used. Okay, and if you look at the criteria, is almost the same that what we are targeting when we talk about electroactive materials. They must produce high electric conductivity, high thermal, excellent optical properties, and more resistant to chemical changes. Because if you look at these carbon nanotubes, if you look at the structure themselves, it shows a very strong, like what, our piping, our piping system, they use this hollow carbon, right? So which is actually very strong, and they can pass through any, any material, any solution, and electron can be transferred easily from one to the other. So this is where, we want this character. The geometry itself can give you some ideas why this material is important. Okay, why the material can give you high electric conductivity. Because from the diagram itself, it shows you that, they have many space, they have a bigger, hollow in between them. And if you talk about multi-layer, you can have a combination of layer that give you more high electrical conductivity. So the size, the geometry, can give you some ideas why is it important in this electroactive material studies. On the other side of it, all right, so a lot of research being studied looking into functionalization. Okay, you functionalize the carbon nanotube. Okay, this is just a carbon nanotube, but looking into some reaction, a chemical reaction, or some reagent used in particular synthesis method, you can functionalize it, okay, to make it more reactive. So some of the functionalization, like called carboxylic, carboxyl, phenolic, aldehyde, and others, it gives you more electrical conductivity. Okay, especially we're talking about oxygen. Okay, they have a free electron pair, so this give more electron density around the surface of the conducting materials. So this will increase the carbon surface hydrophilicity in the aqueous solution. Because we know in the beginning why carbon is important, because carbon can dispose easily in water. Okay, so on the right hand side, you can see a lot of functionalization being made on the surface of the carbon nanotube. They put oxygen, they put nitrogen, they put carboxylic acid, they put a carbonyl group, okay, hydroxide group, and that make the carbon nanotube more active or higher in terms of electrical conductivity. And what's also give you some ideas is that how from carbon nanotube you can functionalize it using a different synthesis method. For example, you want to put some halogen in there, so you can do halogenation, okay? And this also can be converted to more alkyl group, okay, on the surface of the carbon nanotube. When you talk about this functionalization, this will give more impact in terms of surface area, in terms of a reaction with other chemical, because we are talking about materials, they're going to react with another materials, for example, that give more choices to us. That's why we have to think about designing, okay, in the right application use. Okay, so when we do design area of materials to be used, we look into more functionalized materials so that it helps you in terms of your application, different type of application. Either you want to go for corrosion studies, you want to go for sensor, you want to go for other studies of electrochemical method, then it gives you a lot of benefit. So functionalization of carbon nanotube is one of the example. There are a lot of functionalization can be done, okay, not only on carbon nanotube, polymer base, on other carbon base as well is possible. So functionalization is where you can actually tune or design the material to suit your application. Okay, that gives you more of the benefit and also options, you know, to look into other possibilities. The next materials that I'm going to share with you is called polymer. Okay, polymer. We know that in reality, not all polymer are conductive, but doesn't mean that non-conductive polymer are non-electrochemical active. Okay, so polymer is one of the interesting materials that have one excellent chemical, thermal, and oxidative stability. That's one is, I think everyone knows, this is what polymer all about. That's why polymer is very much used, especially in terms of strong materials, like in our car, dashboard, you know, aeroplane. Most of them are using polymer as the base, all right? So that's why polymer is one of the choices. And polymer is considering inexpensive, okay? Because we can start with monomer and we can do a simple chemical reactions to form a polymer, okay? And then we can have different variety of synthesis methods. Polymer also can do different synthesis method. We can do a chemical method. You can also do electrochemical method, but oxidizing the monomer to form a polymer or reducing a monomer to form a polymer, okay? And also we can do a lot of method like sol gel. I heard that you have actually heard about it. Sol gel, sonification, and so on. So there's a lot of synthesis method. Easy chemical modify, because most of our polymers have conjugated or have functional group in there. So it's considering easy chemical modify. And then they also have a background of ideal platform for immobilization of constituent materials, because the backbone of the polymer itself shows quite stable, okay, that give the features of immobilization. In other words, it stays on the condition, okay, and more stable. So then moving on to conductive polymers, okay, these are the examples of polymers that normally use. I think for undergraduate and postgraduate students, we usually give these polymers because from the list of polymers that I'm showing here, it shows, you know, one, a conjugated system, okay, they have a double bonding towards the backbone. They also have functionality, for example, nitrogen, okay, and also like sulfur over here. So we use a different type of polymer backbone so that it gives some character to the polymer building, okay? So we, like thiophene, polythiophene have sulfur character, polypyrrole have nitrogen character, and so on. So a lot, you know, they're quite examples of polymer use, and you can get it for in a reasonable cost, okay, to start with some polymers. Moving on to this, we are talking about conductive polymer, okay, because we are talking about electroactive materials. So we want a unique electrical features, that one of it. Moving forward, we want excellent physical properties. We also want excellent chemical and thermal stability and practical in common solvent, okay? Because we have a different application, okay? We want to combine with others, for example, like what we have done with polyaniline and silver nanoparticles. We drop cast only on the top of substrate, okay? So we want them have a special feature. So we are moving to conductive polymer. One of the examples that I'm going to share with you is polyaniline, PANI, the one that also my students, quite a number of them are also working on PANI. Why PANI is one of the conducting polymer of interest? One of that is because the conjugated polymer based on heterocyclic aromatic units on the main chain. Okay, we have heterocyclic is conjugated system, aromatic, one of the also criteria, because we know that it's electron can transfer between the aromatic rings. Okay, and it's more stable, and it can be synthesized chemically or electrochemically. Okay, so the polymerization method can do chemical or electrochemical. So we see by having different parameters, different setup of the experiment, we can have a different size, okay, of the polymer. And then we have a greater opportunity to functionalize, okay, because Pani have nitrogen, a group there, okay, it's greater to functionalize by replacing the hydrogen. And we have also high conductivity and excellent chemical stability. And it also can act in a large voltage window. This is also important. In electrochemical studies, when you have some targeted molecules to be reduced or to be oxidized, this is one of the behavior of the materials that need to be emphasized as well. We want them to have large voltage window. For example, that material can form in the condition that we have a very extreme positive voltage or very extreme negative voltage. So we see the performance of the material in large window, okay, maybe 3 to 4 volt, for example, it depends. So then this is one of the character that we also have to look into. The other one is a corrosion protection of current collectors. This is being used, so mostly polyadenine used in corrosion protector, okay, and flexibility and lightweight. All right, so this, I think the behavior of the polymers always been taken into this consideration. What are the advantage of this? Okay, so easy to construct, okay, compatible with other devices, more application can be done, okay, can be controlled to the properties of the polymers. And then, for example, if we want to fabricate to form a sensor, we can consider using Pani is inexpensive because easy to synthesize, and then it's not that very expensive monomers. And from there, we can actually consider the sensor built from Pani is not very expensive, it's inexpensive. So this is one of the examples of conducting polymers. So if you look at other polymers, okay, why polymers is one of the group of materials of interest in electroactive materials, because it can have different morphologies, okay. It forms a different morphologies, depends on method of preparations, it depends on the type of synthesis, and they can form varies. For example, they can form as nanofiber, they can form as nanowire, they can form as nanospheres, nanotubes, ultra-thin film, and so on. So by controlling a different fabrication method or different synthesis method and different conditions of the synthesis method, you can actually control the size, the geometry, and whatnot. Okay, so that's why electroactive polymers, or conducting polymers is one of the area that of interest, because it gives more stability because of the long chain backbone of the polymer itself. Okay. Okay. The other one that also of interest, okay, when we talk about electrochemical nanocomposite synthesis method, when you do a 3 conventional cell, which is this is a very simple, we start with a very small amount of material. You can use a simple 3 electrode system. You can do electrochemical synthesis of your material of interest. Okay, so the simple fabrication method, okay, like what I'm showing on the right hand diagram. So in this case, we do electrochemical fabrication, basically looking into electrochemical synthesis of the material, and then you can use it at room temperature. Okay, if you want to do it at different temperature, you can have a different condition, or you can do it thermally, or you can do it like in reasonable temperature, so that you can actually make the cells or reactor in different ways, so that you can control the temperature. And then the film thickness can be easily adjusted by varying either the current or potential with time, because we're going to use a different electrochemical methods. By, for example, by putting in constant potential, or constant current, or do a potential scanning, or we call it sweeping techniques. So these are different electrochemical methods. I hope that the students have actually got some information or some training by the docent, where you have a different techniques, like what we call it potentiometric measurement. We have voltammetric measurement. We also have linear sweep voltammetry and whatnot. So these are the condition that you can put into the system so that you can form a material using this, what we call it, electrochemical synthesis method. Okay, so by having this a small amount of materials, you can actually produce nanocomposite synthesis using this technique as well. So this is one of the approach that is one of the potential approach that can give you some ideas of how we can actually synthesize this material. Okay. The other example of thermal and hydrothermal nanocomposites, this method. When you talk about thermal and hydrothermal, definitely using temperature, okay, different temperature condition. So when you talk about different chemical temperature difference, you need to control the temperature. So basically you have a buffer area where you can actually control the temperature. Okay. So if you do it in a bulk material, you can use a reactor, because some industry call reactor, but in laboratory we just call it cell. But definitely for temperature control, we use a stainless steel covers so that it can maintain the temperature inside the electrochemical cell. We can use it thermal only or hydrothermal, means include water or other solvents, so both can be done. But again, in this particular case, we want to make sure that it's protected, so not then we can have a constant temperature in the electrochemical cell. So this hydrothermal synthesis is a technology for crystallizing materials, okay, directly from aqueous solution by depth control or thermodynamic variables like temperature, pressure, and composition. So we can have a different temperature in fabrication, and then it will affect the properties and morphology of the composites. So at the end of the day, you can have your composite and you can actually characterize it, and then you can actually measure what are the size of your nanocomposites. So normally in a laboratory, like in the chemistry department, I think we are not call it a reactor. We just use a chemical cell, but it's just a small compartment because you start with the small materials and you can actually cover it so that you can have a constant temperature for this reaction. So why hydrothermal is advantage? And then we can control the reaction temperature. Okay, I think in normal condition we are not using a high oven, okay, or autoclave. But if we have autoclave, which can go up to 800, 900 temperature, is also okay. You can use it. And normally when you talk about hydrothermal, we call it just a one-step synthetic procedure. Okay, it's just one step. And of course, when we cover and make sure it's protected, is environmental friendliness, because is everything intact, okay, in a one-pot synthesis. And then it's good dispersion in solution, because everything is controlled by one temperature, okay, constant temperature, and is inexpensive in material because we are not using that much. We try to produce a nanocomposite with a high surface area, and we can see that it's more reactive. Okay, so these are one of the synthesis method that approach that we do in a laboratory. The other one, we call it sonochemical nanocomposite synthesis method. Okay, sonochemical, basically, you know, we can have a rotation. Okay, this is a simple method where you can actually control the reagent, control the speeds. Okay, and then looking at different condition, you can also do open space. This is very simple setup. Okay. So basically, there are three methods. There are three steps, okay, involved. One is formation, the other one is growth, and then it collapse of the bubbles. Okay, so this is called a sonochemical method. It is based on the propagation of acoustic vibrations, which cause the liquid to produce cavitation bubbles of high density acoustic energy. In the ultrasonic dispersion procedure, symmetric violations of the cavitation bubbles in the interfaces cause the bubbles to collapse. When the solution is exposed to ultrasonic irradiation, the bubbles in the solution can be eliminated by using its acoustic fields. It is also utilized to introduce shock waves in the solution and accelerate the impact of the liquid on the surface of the particles. So this sonochemical technique has proven to be a valuable method for obtaining material of smaller size and higher surface. So these are one of the method that can be used, it's called sonochemical method, to produce a nanocomposites. Okay, so from here, it depends on the vibration, okay, the rotation, okay, of the solutions to form bubbles, and from there, you can see that the from the ultrasonic dispersion, so it can form some nanomaterials, and you can actually measure that from different methods. The final one, okay, looking at physical chemical methods of nanocomposite synthesis, okay. So basically, if you look at overall, okay, overall that I've actually shared with you, okay, the whole methods of the production of the nanostructural materials, basically it involves physical and chemical. Talking about physical is normally involve the reaction condition. For example, either we use a mechanical, or stirring, or temperature different, or pressure different. And also we're looking into chemical, which involves some reagents, some chemical reactions, okay, that can convert the structure to be the targeted final structure that we want, either in the form of nanostructures or microstructures and others. So this actually can give us some ideas of how we should fabricate our materials. So from there, we can see different geometry produced, different size, okay, different diameters, okay, of the target nanomaterials that produced from this different. So I've actually shared with you some of the synthesis method, okay. To summarize everything, we can see that, we can do a chemical, electrochemical, thermal and hydrothermal, and also sonochemical synthesis method, so that we can understand how at the end we can actually produce that different type of nanomaterials. Then we move on to the other type of material. We call it metal. Metal, by chance, is actually naturally occurred, all right? And then you can have a different size on Earth, or you can also try to purify it if you look into a different surface area. These are some of the examples. So most metals have high effective surface area. Metal by itself is also conducting, all right? So, and then by having different size, you can actually increase the surface size, and you can also increase, the mass transport, okay? By having a smaller size, you can have a higher mass transport. You can control the size as well, depends on your application, okay? You can have also optical properties, and then you can also have chemical electrical features, and this is effective usage of expensive compounds. Because some metals are expensive, some metals are reasonably priced, okay? You can have it on Earth so that you can extract and get a different type of metals. And you can form in different metal size as well, depends on how you purify the metal and what are the technique used to actually extract it out from combination of metals. For example, you get from rare earth elements, for example, it's actually a mixture between different metals, okay? You have to extract, selectively extract certain metals. From there, you might have different sites of metals, okay? So this again have to be explored in different ways. But metals is common, okay, to use as conducting materials, and metals directly can be used, for example, as your electrode, okay? Without doing any modification, you can directly use that metal. But what interesting, okay, in the coming years, when we talk about science and technology, they are looking at metal organic frameworks. Why metal organics framework is of importance, okay, because it has a different features, all right? If you look at the right-hand side of the diagram, you have a metals, and when you combine the organic molecules, organic linker, you can have a building structure, which have different properties. For example, they have space in between, they have link in between, and they can have a very stable, okay, structures. So that's why metal organic framework is one of the current approach in looking at potential electroactive materials. So just to go through this to understand more, owing to their compositions of one or more traditional metal-based ions and a combination of different organic ligands, a unique advantage of electroactive frameworks compared with many traditional inorganic materials is the potential access to a multitude of different redox states. If harnessed, the varied functions of these states as a result of their distinct structural, electronic, optical, magnetic, fluorescent, and host gas properties underpin a wide range of potential applications in which electroactivity and nanoporosity within a solid material is a significant asset. So because it gives a space in between that makes them more combination of properties, can be applied. So that's why metal organic framework is one of the way forward that we should actually explore more so that we can have a high impact in terms of the electroactive materials. So basically a two synthetic approach, okay, is quite straightforward if we look at here, okay. And this performance can also be improved, you can further improve by having this and combine with other electroactive materials like reduced graphene oxide. You can also combine other composite like carbon nanotubes. You can also combine it either with metal nanoparticles and whatnot. Because if you look at the structure, itself, it gives you a space in between that because of the linker. Okay, it can give you more space in between, but at the same time, it gives you more stable structure that give you possibilities, because one of the criteria that you want to produce as your electroactive material, it gives you more stability. Okay, so these metal organic frameworks can give you more stability to your composite material. So these are some of the examples that you can combine with metal organic framework so that it gives you more impact, okay, to the reaction or electrochemical reaction can happen at the next level of application. So just to give you our examples, this is our work. This is my student, my PhD students' work, where the example that I've given much earlier to all the students, that we can use a different preparation method or different fabrication method. Either you want to use a chemical reaction modified using any different reagent, or you can use a sonochemical or hydrothermal methods, okay, or you can also do electrodeposition method. So different method can give you different novel solid phase nanocomposites, and then it gives you a different behavior, different size, different morphology, so you can actually control the preparation method so that you can have your target, because certain application might requires a different morphology, different stability, different electrical conductivity, and so on. So you can have a different type of method. And then these are one of the examples, okay, where the students do a polymer-based nanocomposite, a carbon-based nanocomposite, and with these two combination, you can also cross-link one to the other by different preparation method, so that at the end of the day, you can have a different composite style with different morphology and different size. Okay, so these are some of the examples that we have done in our laboratory. It gives a very good input. At the end of the day, with this material later, I will share with you how they can actually be used as electroactive layers to detect certain analytes. Okay, so these are why we are looking into different material types so that we can give some ideas on the usage at later part. So my last slide will be on the future outlook, okay, because there is a lot more and opportunities we can study on these electrode materials, okay, a lot of challenges in the future, but there are a lot of possibilities that we can work on, okay. Because if we're talking about material, is never end. We have a different type of material, exists in the nature that we can use. Okay, so what important here, if you look at the way forward, we know that we can form different dimensional shape, size. Okay? We can have a different character. Okay, but all in all, they are very important to look into charge transfer phenomena in three-dimensional coordination space, because we look into a three-dimension. Okay, how we can actually do modification, how we can do, we can tune the structure, or how we can actually functionalize the structure where we are looking into three-dimensional. So we can look into the ability for this relationship between the structure and also with the function, okay, of the electroactive frameworks, because these are very important to give us some ideas whether we want to do hollow size material, we want to do spheres, we want to do like scaffolding structures, or we want to do a different type of geometry. We are looking into tri-dimensional coordination space, so that we can think about how we can actually do some modification of the structure. The other one is, we know that one of the factors that can give more option for future work is on the tunability, and we can tune the structure, okay, on certain application. So this will give you more multifunctional properties. Okay, for example, this material can be used for battery application, for example. But on the other hand, the same material also can be used as a membrane for sensor, for example. So by having one sample material, it can be tunable in such a way that it's easy to tune, okay, and can be used in multifunctional properties. Okay, then a lot can be exploited, okay, especially in the gas separation or storage or whatever. There's a lot of and people talking about optical and magnetic properties. These are some of the examples can be used to use the material. And the other one is, if you look at the overall fabrication method that we can use, one of it we are doing electrochemically. Now, the electrochemical method can be used in situ or ex situ, depends. When you talk about in situ electrochemical experiments, is where you can actually bring the material or samples to the field. Okay, so you can use directly. Okay, and you can get the results immediately, because one of the factors that influence the best electroactive material is where it can give you fast response. So we can do in situ, okay, or ex situ. So this is one of it. And the other one is flexibility of the frameworks, like what we've seen. One of the example is metal organic framework, where you can see that you can actually do your own. If you want to build up a scaffolding or what different geometry and different for application, and you can see that it is also possible, okay, for us to do more design on this. And finally, not to forget that nowadays people talking about all these computational, okay, calculations, simulation, AI, and so on. So these are also one of the things that you can also venture in when you have a big data, large data on the performance of your material. You can expand it not only to do a calculation, computational calculation, but maybe to have different analytics, okay, on your material of study. This one I never had an experience. I'm not going to go more details, but I see there are more can be done for future. So for that, I think, thank you very much. I would open for any discussion or any question by the students. Thank you.
Okay, thank you for your interesting lecture, Professor Yatima. So now is time for questions. Okay, students, you can ask directly to Professor Yatima, or you can write down your question in the chat room. Okay, Mario.
Okay, thank you, Mr. Bowo. Hello, hello, Professor Yatima. My name is Mario. I'm currently a third-year student at University of Indonesia. I have two questions for you here. In one of your slides, Professor said that carbon nanotube is more resistant to chemical change than graphene sheets. And my first question is, why carbon carbon nanotube is more resistant to chemical change than the sheets graphene, and what factor make it happen? And my other question is, between carbon nanotube and graphene, which one has the better electroactivity, since both are carbon-based material? That's it from me. Thank you.
Okay, very good questions. Okay, if you look at carbon, okay, carbon by nature they have 4 bonds, all right? But when they form a different formation, you know, they can have a free electron where they can actually play an important role, okay, and more active in terms of the electron density around the carbon base. So that's why, you know, we are looking into more like 1-dimensional or 2-dimensional, 3-dimensional, depends on the formation. So if you look at between the carbon nanotube and also graphene, you know, graphene is actually layer by layer. Okay, you can have 1 layer, 2 layers, and different layers. But when carbon nanotubes is a tube, okay, it's a tube. By formation, by geometry formation, you can see the difference. Okay, one is tube, one is layer by layer. All right. So if you look at the behavior of both, you know, there are some differences in such a way, because we have one equipment here in Simlaya where you can form a layer of graphene sheet, 1 layer only. It's a monolayer graphene sheet, which have a very high surface area and very active, right? Because we can form 1 layer or 2 layers or 3 layers. So it can form a very active layers. It depends on the application, because for me, when I look at different application of the material, I can see both have a different character that can be used in certain application. Okay, for example, we're talking about graphene oxide, for example. We are looking into the mixtures, you know, they can easily be mixed with other metal base, for example. But when we're talking carbon nanotubes, when we want to do a functionalization, we also have, it's not straightforward, you know. Looking at the synthesis method is quite straightforward, but it's more challenges, okay? Because we want to see a homogeneous covering of certain functionalization of carbon nanotube, okay? So in some cases, we cannot get a homogeneous covering on the carbon nanotubes. So then we have to play another role to look into the fabrication method. Okay, so that's come into the whole idea how we're going to design what are the functionality that needed to be done between the carbon and also the graphene. So that's give some example, but what we need to understand here, because when we do some modification or tunable properties of that carbon base, we have to look into the actual application that we want to use for that, because it's a broad area. We cannot see that, okay, using this carbon nanotube is the best for this application. Using graphene oxide or graphene or graphite, on the other hand, is good for the other application. But for me, throughout my journey using carbon base, I think they have their own strongest part of why we choose that as our carbon base in terms of moving on to more composite type of material. I hope it answers your question.
Thank you a lot, Professor. It's answer my question.
Thank you.
Okay, any other question from students? Okay, if you want to write down your question, that's okay.
Yeah, you can also write in the chat.
Yeah, in chat.
I hope it covers your topic.
Yes, this is the first session, so mainly about the material and how they are made. Yeah,
Yeah,
Prof.
that's right. That's right. Later, on the second part, I'll show you how we do the modification.
Yeah. Okay. So this is just what punching and question from me to students. Okay. You just mentioned that electrochemical method also has advantage to control size the deposit. Yeah, to control size the deposit. So how electrochemical technique can control the size, and another one is, can we also control the shape of the deposit by electrochemical method, Professor Yatima?
In general, I would say yes. Okay.
Okay.
Through my experience, because okay, when you talk about electrochemical method, for me, it's the best way. Even though to set up the experiment is a bit expensive for a start. Okay. For example, a common setup, okay, of any electrochemical method, we need electrodes, we need potential stat, for example, or depends on whether you want to control current or you want to control potential. And then you need a computer to actually adjust the parameters and whatnot. All right, that's the setup, the simple setup. And then one of the things that maybe is a bit expensive when you want to use different type of substrate or electrode. For example, you want to use carbon base is cheap, but you want to use a platinum, or you want to use gold, and it's expensive. But on the other hand of it, it lasts long. Okay, it as long as you take care of the electrodes, okay, it lasts long. You can do a lot of things, you know, unlike reagents, you know, when you use it, that's it, you know, you can't use anymore. All right. So this a lot of advantage that you can use electrochemical method. And you know that when you do a electrochemical reaction, it's either reducing or oxidizing. So you will control the positions of the potential. Let's say you want to do voltammetric. Okay, so you want to do circuit voltammetry, for example. You can control using potential, okay, to look into how you can actually produce your material. So that's why material that have a large electrochemical window is of interest, because you can control at which potential of your reaction. So these electrochemical methods actually can control the type of material produced, because when you oxidize or reduce, it depends on the electron transfer. You can control 1 electron transfer, you can do 2 electron transfer, 3 electron transfer, depends on the material. So if you want to control the condition, for example, you put in 1 electron, okay, by controlling the right potential at where the 1 electron transfer process can happen, and then you can get that products. But another hand, if you want to do 2 electron transfer, you can also control the end product. So what are your end product that you require to have? Okay, that's one. The second one is by having, because when you do electrochemical studies, one of the factor that has to be always recorded is your temperature. Okay, so temperature, you always have to record your temperature. So by normal room temperature is okay. But again, if you do it in different temperature, you might produce different size of your material. Okay, or even in some cases, we can also get different morphology of the material. Okay, because material is very broad, so you can study that. That's why when you want to do a data collection, you know, if you have a broad area of studies, you can do a simulation, you know, because you have that data in hand. So I would say that using electrochemical methods, you can control the condition, and you can have different methods. Electrochemical methods, I hope that you have actually gone through certain studies. For example, we're talking about potentiometry. You're talking about voltammetry itself. You've got linear straight voltammetry, you have cyclic voltammetry, you have stripping voltammetry. Okay, and then you're talking about also you can do a polarography methods, you can do conductimetry methods. So that where you can control, either you control current or you control potential. So that will give you different, even in different concentration. By nature, different concentration, different morphology, different size. So that will give you options in that. So that's why in control condition, you must have that being recorded when you do the experiment. Unlike the chemical reaction, you normally you consider the concentration or the mole ratio. Okay, you control that condition, and plus you control that one is talking about reagent, and at the same time you also control temperature and pressure to do the reaction. So that's always be, you know, different compositions of materials, different physical factors, you know, while you do the experiment. Again, it also gives you some ideas, you know, when you have a different reagents, you know, what kind of end products that you can get from there. So it's a lot, you know, when you do a literature review on certain areas. For example, you want to combine silver with tanning, plenty literature review on that and with different methods. with different reagents, with different condition, and with different types of fabrication method. So that's where I can give you some ideas on that.
Okay, thank you. Yeah, that's really answering my questions. Okay, there's one question from Nur Amalia Ridwan. Nah, Putri. Okay.
Okay. Thank you so much, Mr. Bo. Hello, good afternoon, Professor. My name is Nur Amalia Ridwana Putri from University, as a student from University of Indonesia. There's something that piques my interest from the modified graphite oxide preparation method. So what I want to ask is, does varying the concentration of either potassium permanganate or sulfuric acid or even phosphoric acid will have effects on the graphite oxide that will be produced from the process itself? Thank you.
Yeah. Then? Your question?
Oh yeah, does varying the concentrations of either the potassium permanganate or sulfuric acid or phosphoric acid will have an effect with the graphite oxide that will be produced from the process of the modified graphite oxide?
Yes, that's right. Yeah, that's right. I mean, that's why we have to control the condition. So as I mentioned much earlier, by looking into different proportions of reagents, okay, and different conditions of the reactions, you can look into different size of graphene oxide actually. All right, because the layer by layer, if you look at here, you know, layer of graphene oxide, it can have a different size. Sometimes it's just break up into small sizes. Sometimes it's have a very to say huge, but you know, you can see it not that huge size, but you know, we consider as nanomaterial is huge size. And at the same time, you can also proceed, you know, with another level by you know, to get a monolayer of this graphene oxide. So that's have a special equipment to get a monolayer graphene oxide. So that's actually a challenging work. Okay, it's not straightforward, but it needs to have more studies on characterizations where we can actually have a different single layer of modified graphene oxide. Yes.
Okay, thank you, Professor.
Okay. Is there any more question from students? Okay. Yeah, there is another one from Robik Firly.
Yes.
Okay.
Thank you for the opportunity. My name is Robik Firly Alfian, as the final student in chemistry department. My question is close to Mr. Bowo's question, but I would like to ask about how to control the modified particles into the size that we want. For example, for nanometer or mesoporous material, especially on the carbon-based material. Is there any specific method in electroanalysis to control that? Thank you.
Okay. Okay. Normally, when we do electrochemical methods, okay, one of the challenge part is to look at, for example, we're using control potential method. Okay, when you do a control potential method, you must understand the behavior of your material. Okay, whatever material, carbon base or other base, because when you do a modification of the carbon base, for example, you're looking into different potential window and where you actually do the modification or other things after that. All right, even polymeric material, for example. So when you do a control potential is very important for you to understand the whole system. And plus, you have to make sure that at the control positions of potential, that one has to be precise, you know, the right potential, not to say precise, but the right potential. It is important because when you do a voltammetric study, for example, you have reference electrode. This reference electrodes must give you the right potential at where the deposition, or you want deposition, or you want to do oxidation, or you want to do reduction. It gives you the right potential. Okay, because if you don't do at the right potential, you might not synthesize the whole materials, or maybe if you want to do only layer by layer on the surface of electrode, you have to make sure that you do it in the right way. For example, you know, if you want to do a polymeric deposition method on the surface of glassy carbon, for example, you cannot see from your bare eyes actually. Okay, you can see some color change, color difference, but you have to characterize it different method. Then from there you can see what are the output from that. So one of the things that can control the condition, to control the morphology of the material bag, you have to control at the right potential. Secondly, when you do electrochemical method, for example, using, for example, stripping voltammetry method, okay, when you scan the potential to more negative or more positive, you must be at the right what you call it, potential. Again, involve that as well. Okay, because that will play a role. What are this will control the condition. The same goes to if you look into the chemical reaction as well. You know, you have to have the right optimized condition. Sometimes people try to synthesize it using 60 degrees C in certain condition, but when we try 60 degrees C, it doesn't work. So what are the things that have to be controlled during the reaction pathway to get the right morphology or the right size of the material? This has a lot to deal with the skills, okay, the skills and the techniques. So you must make sure that the skills and the techniques and the background of work, the literature work, has to be in mind. So at least you know what is your target. You can't just play and try and error in very broad studies, which is sometimes is quite demotivating, because at the end you could not get what you want. So you need to have some literature. That's why nowadays students they try to do, like, you know, they're doing what they call it, some background studies, you know, to look at different conditions and in different size, because nowadays in journals there are a lot of example and work has done on that to get the target molecular size and molecular geometry. So from there, give you some ideas what are the things that certain polymers can behave. Like what you said, carbon itself, they can form as fluorine, they can form as a carbon nanotube, they can form as a carbon nanosheet, they can multi-wall carbon nanotubes. So by having different, you know, condition or reagents or electrochemical properties, so that we can actually tune that into certain character of that material. So that need to be done in a very objective way. Okay. Thank you. I hope it answered your question.
Thank you, Professor Yatima.
Yes. Okay. Thank you. Bu Yuni, maybe you want to ask questions?
Yeah,
Or
actually,
you want to say something?
Yes. Hello again, Prof. Yatima. Nice to have you here again with us. I want to ask just one question. I am interested in metal organic framework. That you said that in your one of your slide you modify the combine the MOF with carbon as a composite as an electrode. Just curious how strong, how stable the MOF on top of that either graphene or graphite or that the carbon, and if you also synthesize the MOF in your group by yourself, yeah, I mean in your group, or you collaborate with other groups at UM. I think that's all. That's my question. Thank you.
Okay, thank you, Dr. Yuni. Okay, actually, the next step of my my interest is actually on MOF, okay, metal organic frameworks, okay, because this one is, if you look at the basic of this MOF, it looks like very stable, okay, consisting of stacks of stacks of materials, where you can play around with it. Actually, I got one student previously, right, working in MOF. In this particular case, the challenge is to make it stable on the surface of our substrate. Okay.
Yeah.
Normally, when we do MOF, I think we need to have additives. All right, so that's to give you more stability. We can do it on site separately from the substrate, for example, MOF with carbon nanotubes. But to put it into the modified electrode, okay, later on, that's also another challenge. Okay, so I understand your question. I think that's the step that gives us more challenges. That's why, but the most important that we try to get other type of materials so that in future we might have solutions how we can actually make it stable on the surface of substrate. So that will be on the modified electrode part. Thank you, Dr. Yuni, for your questions.
Thank you. Yeah. Thank you, Pak Bowo. Yeah, at the time.
Okay, I think the time is up, Professor Yatima, and I hope this will give an insight, for our students how to do or how to conduct research, especially in electrochemical in electrochemistry. And this is just the first part, and we have still more, two part more. Okay, so we will get benefit a lot of from Professor Yatima, I believe. So yeah, before we end our sessions, would you please, students, turn on your camera, and we will take a picture for the documentation.
Are you still having virtual classes or you have mostly physical classes?
No, we have now actually mostly offline.
Classes.
Yeah, offline. Yeah. Oke. Pak Ridwan mau ambil foto atau saya?
Siap.
Saya Pak.
Oh Pak Bu Safira ya. Oke.
Baik, mohon untuk semua partisipan untuk on cam. Mari kita foto bersama. 1, 2, 3.
Saya sendiri malah belum.
Ya.
Pak Bowo missing. It's already.
Mbak Safira di mute, Mbak, nggak kedengeran suaranya.
Oh. Ya, ini masih slide 3, Pak.
Sudah?
Oke, baik. Sudah, Pak. Terima kasih.
Okay, thank you, Professor Yatima, and we will have the lecture of electrochemical method with Professor Yatima on Monday, on Monday 8 o'clock in the morning or 9 o'clock in the Malaysian time.
Yes.
So we will see you again, Professor Yatima.
Okay. All right.
Okay,
Thank
bye.
you very much. Okay. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Prof.
Thank you. Sama-sama. Selamat berpuasa ya.
Selamat puasa, Prof.
Ya. Berpuasa ya.
Terima kasih Pak Bowo, Bu Yuni.
Sama-sama.
Ya.
Ngerjain maaf tuh Bu Yuni.
Oh, iya.
Kayaknya ngerjain maaf juga ya.
Bantuin Bu Ivan bikin elektroda juga, makanya penasaran dia bikin stabilnya gimana.
Okay.
Ada alasan ke sana dong, Cie.
Sip.
Oke deh.
Okay, yuk, bye.
Makasih Pak. Bye.